Hello guys, today I'm going to record the first half of last Tuesday's class that was accidentally not recorded. And I'm just going to go over and explain the notes that were posted, but it should be it should hopefully go pretty well. So this section of the class, we're talking about energy balances. And in the previous class, we had derived a general form for the energy balance. Now, if you remember, we started talking about how the energy balance would now be incorporated into our problem solution and be coupled or um, be solved simultaneously with the mole balance. And the energy balance we derived was Q minus shaft work. In this course, shaft work is often going to be zero unless you're working with a polymer where you have to put in a lot of work to mix it. This is heat coming from, for example, a jacket, a coil, or a heat exchanger, minus shaft work plus the enthalpy, the molar flow times enthalpy in minus molar flow times enthalpy out, and that's equal to the energy of the system over time. The Here we are also using pure component enthalpies because we're assuming there's no enthalpy of mixing. So we're using not an average enthalpy, but pure component enthalpies. That's going to come back just a little bit later as to why we can use pure component enthalpies. And we did some derivation and found and derived this form, which is the general form of the energy balance, where this term here, those two terms, get manipulated to give this term here on the left, which is the sum of all the flow n times an average CP of each species with the temperature difference between the reactor temperature minus the inlet temperature. This is essentially the rate at which you need to heat up your feed to the reactor temperature, or how much heat do you need to remove from your feed to bring the inlet temperature to outlet temperature or to reactor temperature, right? So reactor temperature would be in a CSTR, to outlet temperature would be in a PFR, okay? And the term on the right, this is the heat of reaction times conversion. So this is the heat that goes into converting the substrates to products, the reactants to products. So these two terms taken together are the overall enthalpy of reaction. So you bring your reactants to the temperature of reaction and you react them to form products. So these two terms come from those up there. Now, this is a complicated looking equation, but we can simplify it greatly. Say, for example, a single reaction where K is equal to 1. So you can actually write eta, in this case, as Fa minus Fa naught over nu A. This is a single reaction of A going to products. And you can solve for eta equals Fa naught Xa. And if you base your reaction on A, so that means eta nu A is equal to -1, and Xa is Fa naught minus Fa over Fa naught. So this is how you can derive the relationship between eta and Xa, right? Eta is Fa naught times Xa. And you can plug this in and you can derive a single reaction heat energy balance. Keep in mind here that this is derived for in terms of molar flow rates for a continuous reactor. And in this case, at steady state, du cis dt is equal to 0. You can also have a derivation for reactors in series where you have multiple reactors. And you can have it for, you can also have it for in terms of eta, where this term here essentially becomes a summation So these are reactions. So these are multiple reactions happening together. And for each reaction, you'll have an eta that would go from out of one reactor, eta naught K. This is the reactor you're dealing with, and this is eta from the previous reactor. Okay, so this is essentially sort of explaining, giving different forms. But in this course, we'll mostly deal with the single reaction form, and we may look at a series of reactor forms in a couple of lectures, or maybe probably 2 lectures at this point. So the one term we need to really look at is the heat of reaction which is a function of temperature. So that term we're going to look at a little bit in depth. And this is from thermodynamics, where the heat of reaction at a certain temperature is the heat of reaction at a reference temperature. We call it delta H naught at a reference temperature, plus an integration from the reference temperature to a final temperature of stoichiometric coefficient of each species times the heat capacity of each species times the temperature difference. And this heat of formation at reference temperature is a summation of stoichiometric coefficient of each reactant and or product of each species times their heat of formation of each species. And this is all from thermodynamics. So here, what you can open up this term, and if CPI is constant, which is the heat capacity of each species, is constant, then you can simplify this term by taking CPI out of the integral. So that's the first thing you can do, and you can integrate from your temperature desired. You can basically have a difference between the temperature of your reaction minus a temperature of reference. There's supposed to be an average bar, a little CPI bar here, so I forgot to put that in. But if CPI is not constant, CPI is a quadratic form, which you can find the alpha, beta, and gamma terms from a handbook. So for example, if you have the reaction 2A plus B equals to 2C plus D, your mu I CPI T minus TR is essentially 2CPC plus CPD minus 2CPA minus CPB, and that's times T minus TR, and this is often called delta CP. So that's another way to call the mu I CPI, which is often called delta CP. So we can look at an example where we want to calculate the heat of reaction at a certain temperature. So we can look at ammonia synthesis, where the heat of reaction at 150 C, that you want to calculate the heat of reaction at 150 degrees Celsius. You're given the heat of formation for each of the species. Now, this can be looked up, but it's zero for single components, such as nitrogen and hydrogen. The heat of formation is 0 for these. So you can calculate the heat of reaction at a reference temperature. In this case, I think it's 298. And this is basically the heat of reaction at a reference temperature, right? You're also given in the problems CP for each species in calorie per mole K. Here, the heat of reaction is solved at calorie per mole nitrogen, because we chose nitrogen as the basis for the reaction, so that we can easily scale up. If we have 2 moles of nitrogen, we can multiply this by 2. So it's often good to do the heat of reaction at the same basis as the reactant that you choose to do your mole balance, for example. So it's always a good practice. So here we can calculate delta CP, right? So this is 2CP ammonia minus 3 Cp hydrogen minus 3 Cp nitrogen. So this is this minus 10.12 calorie per mole K. We can now calculate our heat of reaction at 150, and that is the heat of reaction at a reference temperature plus the delta Cp times T minus Tr, and that gives us minus 23,000. One thing to note is that the heat of reaction between 150, between 423 Kelvin and 298 Kelvin is almost constant. There's not a big difference between these two numbers. So you could often assume that the heat of reaction is independent of temperature if the range of the temperature of the reaction does not change it too much. And the other time that you can assume that the heat of reaction is independent of temperature is if delta Cp is equal to 0. Delta Cp can be 0 if you have a reaction of A goes to B or reversible reaction A goes to B. So it's the same if you have a reaction of A going to B. So then Cpa is equal to Cpb. So if you have an isomerization where Cpa A and B are quite similar, so their heat capacities are quite the same. So you can have a system where delta Cp equals 0. Okay, so when delta Cp is equal to 0, you can use the heat of reaction at a reference temperature in your energy balance. So you can use that right here. Instead of putting delta H of reaction at T, you can put delta H naught of reaction. Okay. So we can also write the energy balance for different reactors and under different operating conditions. We're going to look at them first for different reactors. For example, as we mentioned earlier, this form of the energy balance for CSTR, packed bed reactors, and PFR, it's dus dt is equal to 0. Okay, what we'll look at with PFRs and especially with packed bed reactors, we will make a slight change in the energy balance to do it as a function of reactor volume. So you can actually derive a differential equation starting essentially from this form. If you take the derivative with respect to volume, you can write the energy balance for a PFR and a packed bed reactor. In a moment, we'll do that next class. So for a batch reactor, this is derived in the book. The heat added or removed here is going to be equal to this. This term is essentially the same as that term, but now you're dealing with number of moles instead of molar flow rates. So it's a summation of 1 goes to n. So these are the number of species in your reaction of Ni times their heat capacities times a change of temperature as a function of time. And this is plus delta H of reaction T times Na naught dxa dt. One thing to note here is that Na naught dxa dt is the same as minus RAV. So this is from your design equation. So what you can see is that your design equation is embedded in your energy balance, okay? So this is the same here. So if you look at eta K, this is essentially from your design equation. Your mole balance is embedded in your energy balance. And yeah, so you can rewrite this as Q is equal to summation of Ni CPI average dt dt plus a minus RAV times the heat of reaction at temperature T. But once again, in many cases, we'll find that we can replace this with the heat of formation, the heat of reaction at a reference temperature. So now that we have the two, some of like a batch reactor form of the heat of the energy balance and more or less a form for energy balance for CSTR. And like I mentioned, there's a slight change to make it for a PFR, packed bed reactor, especially when the heat exchange term is not 0. So we'll work on that next time. So now we can look at the energy balance, how we can modify it under different operating conditions or different common reactors. One first approximation is adiabatic. Adiabatic systems, meaning that you're not adding or removing heat. So Q is equal to 0. One thing I should apologize for is sometimes it's actually supposed to be Q dot because it's a heat rate. So it's some amount of heat per time, right, per seconds per minute. Because in the case of, in this case here, you have molar flow rates. So these are per time. So it's, in this case, the heat added is going to be per time for a flow reactor. Now for yeah, it is the same here actually. It is also per over time. So these are supposed to be Q dots, not Q. But it's fine. Just wanted to make sure I clarify that. And now, if delta Cp is equal to 0, as in the CPIs are constant, and they are equal for reactant and product, then you can rewrite this and solve for XA as a function of temperature. This is very important because here you have a way to relate your conversion to your reactor temperature or to your reaction temperature. And for an exothermic reaction, you can see that as the temperature goes up, your conversion goes up, right? So you can see how this works. And then here, delta H would be a positive number because the delta H of reaction for an exothermic reaction is negative. So minus minus would be positive. So you can also solve for the temperature of your reaction, same by basically solving for T instead of XA. You can solve for what is going to be the temperature of your reaction at a certain conversion. Same here. And once again, you see that for an exothermic reaction, this number is positive. So the higher the conversion, the higher temperature. For an endothermic reaction, this number is negative because delta H of reaction is positive. So the higher your conversion, the lower your temperature. And but I put a form here where delta Cp is not 0, so you can see how XA would be. You can solve for XA there. But solving for T is a bit more tedious, I think, but it's not, it's just a bit more algebra. So you can do the same for a batch reactor. In this case, it's the exact same form, except that instead of FA naught, you have NA naught. Instead of FI naught, you have NI. You have NI naught instead of those. So you have those two terms. A more general way, especially if you're dealing with gas phase, for example, could be to put it in terms of mole fractions. So you could also do that. Now, one thing you can notice is that the denominator is all flows, not just the ones that participate in reaction. The numerator only really deals with the ones participating in reaction because they're multiplying the heat of reaction. So that means you could add it also accounts for inerts or solvents added to the reaction. So that means if you have an inert, you can think of this. If a reaction is A goes to B and you're feeding pure A, this is gonna be FA naught. But if you're feeding A like half and half with an inert, this is gonna be FA naught plus FI naught. And in this case, this term here is going, the slope is, you can think of this as a slope of a line, right? This is the intercept and this is the slope. So the slope is going to be lower if you add an inert versus if you have pure A. Okay, and the last thing to note is that, last thing to note is that this term in red is often called the adiabatic temperature. So it's an average TAD is often called the adiabatic temperature because this is the units for this are temperature, right? Because this is say, Kelvin. The units for this slope are also going to be Kelvin because XA is unitless. So this is often called adiabatic temperature. Okay, and then you can graph this, and you can see that it's a line that starts from T naught and goes to T as a, if you graph XA as a function of TA, as a function of T. But this is valid if delta H of reaction is independent of temperature, and if delta Cp is, if Cp's are independent of temperature. So if you have an average Cp, okay. So this is why it's aligned, because otherwise it's going to be complicated, right? Because Cp's will have temperature terms which will be integrated over the temperature increase or decrease. So this is the form of the energy balance here if there's no heat added or removed. Now we're going to move on and look at if you have a CSTR with a heat exchanger, and this heat exchange can be with heat exchange, it could be a heat exchanger, it could be a coil, it could be a jacket. And the Q term will have a form that is UA T A, for example, this would be a T of your coolant or your heater minus reactor temperature. Okay, say if you have a large coolant flow, TA is constant. This picture shows here if you have a CSTR and you have a large jacket with a coolant flow that is very high, the temperature of the coolant will not change very much. And here you can calculate your conversion in this way. So this is all manipulations of the energy balance. And lastly, but we'll get to all of these forms in the next two lectures. And lastly, we can look at a packed bed reactor or a PFR with heat exchange. So if we look at a packed bed reactor with heat exchange, so you have here your packed bed reactor with the green catalyst, packing in there, and there is a temperature of T naught and a flow of FA naught, molar flow of FA naught going in, and then out you have T and FA. Now on the outside of your reactor, you also have a coolant or a heater or heating fluid that is flowing either concurrent or countercurrent. And when we're going to solve these differential, you're going to solve these mole and mass balances accordingly if it's co-current or countercurrent. Okay. Now, this is what I meant earlier by making a small change to the heat, to the energy balance. We can derive this equation, where if you look at, this is for, let's say, a PFR, the change of temperature as a function of volume. So dT dV, as the reaction goes along, the temperature will change. It's going to take the form of heat generated minus heat removed divided by a summation of molar flow rate. These are not FI naught, these are FI. So this is derived from taking a slab of the reactor, similar to what we did for PFR mole balance. And we're going to do a temperature balance across. And for example, one simple form of this could be dT dV. This is the heat generated from reaction minus heat removed by a heat exchanger. And here, TA is the temperature of the cooling fluid. Now, TA can be constant. TA can also have its own balance because it changes from inlet to outlet. And we'll look at all these forms and do examples of those. All right. So I think that's where we were, and I wanted to kind of wrap up a little bit in this part. So what the big question is, how do we solve problems that involve energy balances? And like I said before, we have to find ways to couple the energy balance with the mole balance, the rate law and stoichiometry. So this is essentially our little tower, which builds upon our initial first few chapters of mole balance, stoichiometry, rate law. We can have pressure drop as well, and then we add our energy balance and we can combine everything. For example, if you have a simple reaction of A goes to product where minus RA is just KCA, you can write that rate law as, by plugging stoichiometry, but now remember that K is a temperature dependent. So then you can have a minus RA with, which is K as a temperature dependence. This is K with an Arrhenius relationship. And this would be, this is your stoichiometry of Ca. Now in the gas phase, we would also include, if there's a pressure drop, we would include a pressure drop. And because the volumetric flow rate is also temperature dependent, we will also have a T naught over T term, for example. And I think I made a mistake here. Yeah, it should have been, there should be also an expansion term, say divided by 1 plus epsilon xa, right? The expansion term I forgot to add there. So if you think of that now, if you're dealing with an adiabatic reaction, that temperature term that is here is given by this algebraic relationship. So you can remove temperature from your equation completely by substituting temperature, unknown temperature, with known terms, but in terms of XA, right? So you could plug this here and solve everything as one in your design equation. So you can have a system where you plug all of this in your design equation and you can solve your mole balance in this way. And there's an example in the book that does that. But you'll see that in the book, they have to use some numerical method, or well, we use Python to show these solutions, but they have to use some numerical method to solve these integrations because they are complicated, because you'll have X inside of the exponential and X outside of the exponential, for example. So what we do with Python is that we write all of our expressions and our differential equations. And here there's a mistake. It should be FA naught dxa dw equals minus RA. I forgot the FA naught. And then we ask Python to solve them simultaneously and plot them over a certain reactor volume or catalyst weight. And that's how we solve for these relationships. Okay. So that is where we had been before we went on and did an actual example to show you how all of this works. And yes, so, yep, thank you guys.